let's see. Is that full screen for you guys?
Yeah, I'm gonna, for Twitch viewers, I'm gonna cover our faces so you can see it.
Okay, I'm gonna, well, we don't have a ton of time, so I'm gonna go fairly quickly. Please feel free to ask me to slow down at any point. So yeah, obviously just the imports and then the data loading, which is basically just copied from the other example scripts. This is just some initial summary statistics. You can see that, yeah, the new feature names are pretty interesting and fun. Hopefully there's nothing offensive in there.
We'll see.
We'll see. Yeah,
give the folks a little time, they'll find it.
I don't think I've actually read all the 1,000 feature names, so won't be surprised if someone finds something funny. So yeah, there's now 20 targets. You can, if you just look at the correlation of all the targets with each other, target is exactly the same as target Nomi currently. We may change that in the future, but hopefully we will get true contribution out before we ever have to change the target you're scored on.
Excellent.
You can see that the targets are there's a whole range of correlations between the targets. But it's kind of interesting just looking at like target Nomi and target Nomi 60, they're only about 50% correlated. So just going out to using a much longer window changes your target quite substantially.
Mm-hmm.
So there's now 1,050 features, and things are not broken into feature groups anymore. Although if you just look at the feature by feature correlation matrix, you can see some pretty obvious patterns. And so you're welcome to make your own feature groups, either by just breaking things down to the most obvious pattern here, or yeah, doing other sorts of correlation-based or clustering-based feature groups. There's a lot to explore there. Let's see. So this is just showing some of this is just identical to the previous notebook. This is just showing how many stocks are in each of the eras.
That looks very similar to the old data set.
Yeah, yeah. Because it's basically just a higher. The same thing but sampled more densely. So the standard target, the target Nomi you guys are familiar with, has this distribution where you have 5% in the extreme bins, 20% in the second in bins, and 50% in the middle bin. Some of the new targets have different distributions. For example, some of the targets have 7 bins, and you can see that the percentages in each bin are not exactly constrained in the same way they were. So these targets were constructed a bit more flexibly, and you can see that even between the ones that have 7 bins, there could be some differences. So this is just showing that, yes, some of the features are very correlated with each other, and in some eras even potentially perfectly correlated. But this correlation can change over time. So if you just look at the correlation of features in the first era and the last era, you can see that what was perfectly correlated in the first era becomes negatively correlated in the last era. So that's something to keep in mind. Features have some predictive power just by themselves, but this is just showing the correlation for one era. And if you look at a given feature and look at it across eras, you can see that the pattern, how correlated it is with the target, can vary a lot era to era. And so you can think of that as a feature working or not working depending on the era. And this plot is similar for all the eras. There's no feature that consistently has a positive correlation with the target. That's just life. So I mentioned this a little bit earlier, but the feature exposures of different targets can be very different, even orthogonal by construction. But if you just compare like Nomi 20 to Nomi 60, the feature exposures of those two targets, and the feature exposure is about 67% correlated. And you can see that there's some pretty substantial differences. Some of like the highest feature exposures on target on the 60-day target have virtually zero feature exposure on the 20-day target, and vice versa, which is pretty interesting just in itself, just because of the different time period. And yeah, as some targets are by construction designed to have basically uncorrelated feature exposure. So you can, for example, if you plot the feature exposures of Jerome and Janet, you can see that the feature exposures are basically completely uncorrelated. This is basically the same as the old analysis and tips notebook. This is just sort of showing that like your R squared values can look really bad, even though in correlation terms, they're not so bad. It's just, that's just life when you have very low SNR. And you see this is even true with like a gradient boosting model. Like your out of sample R squared values are quite abysmal looking, where when correlations, once you've gotten used to the world of low correlations, they don't look so bad. So yeah, so we keep mentioning this because it's important. Errors are no overlapping. So the target is about the target is basically 4 weeks out, or 20 days out, and the errors are weekly, 5 days. And so a simple way to prevent sort of overfitting due to the oversampling is just to sample every 4th error. I should mention, again, if you're using a 60-day target to prevent that kind of oversampling, you have to sample every 12th one.
Right.
So that's just sample. But if you are sampling every 4th thing, there's basically like 4 ways to do that. You could start sample error 1, error 5, and so on. Then you could sample error 2, error 6, and so on. So there's 4 different ways of doing that, and you could basically build 4 different models and ensemble them. And this example right here is just comparing basically fitting a model on all of the data in the first half of the data set. DF1 is basically just, through a lot of this notebook, we're just fitting on the first half of data and predicting on the second half. We're not touching validation at all. This is all just based on training, which is kind of how we want you guys to treat things. Not look at validation until you're pretty confident in your models already. Try to do as much as you can, just doing cross-validation on training. So this split halves is just a fast way to do cross-validation. But in this example, I'm just basically fitting 4 different versions of the model, just sampling it on 4 different ways. You can sample that with, so you are fitting in non-overlapping arrows. And this is just showing that the correlation score you get on the second half of the data for the model trained on all of it is a little bit lower than what you get with this ensemble. And so let's see. So yeah, so this is just showing, this is very similar to the previous one as well, just showing 4 different ways of doing cross-validation. And so the new thing in here is this time series split groups, which is something we talked about earlier. It's just basically this time series split, but it works with the groups. Because previously we had just a regular sklearn time series thing here. But I realized that it actually ignores this groups function here without telling you it's doing so. And so it's not doing exactly the right thing. It's just basically choosing an arbitrary cutting point between errors, which could potentially make it a little more optimistic. So this is just a version of that respects the error boundaries. And so you can see that if you were just to ignore error boundaries and just use standard shuffled cross-validation, you can get pretty overconfident. It looks like your average correlation is like 0.051. Whereas if you do something more careful, where you do this group k-fold, where you are only using error boundaries, it's substantially lower. And if you're doing this time series split where you're always only predicting the future, it's a bit lower still. So this time series split groups is it's a good indication of how it might actually do in live, because you're always only predicting the future. When you're doing the group k-fold, you're still potentially using future eras to predict past eras, which could potentially make things look better than they will end up being. But there's good reasons to do both. So yeah, definitely try both. But I would definitely stick to either using the group k-fold or the time series split groups. And also, I should say that when doing this, I had downsampled eras, so only using every fourth era, so there's no overlapping. If you wanted to include all the eras in your cross validation, you'd need to write a routine that makes sure it is purging things at the boundaries of your folds, so you don't have overlapping weeks in your folds, in separate folds.
Okay.
This is the same. This is just as before, basically just showing that the extreme bins, if you're just building a classifier to predict things, you get this kind of odd pattern where the predictions of the extreme bins tend to be correlated with each other. So you can sort of, to model this sort of linear classifier is being able to tell you it's pretty good at telling when something is an extreme bin, but it's not that good at telling you which extreme bin it is, which is kind of an interesting property. And this is just showing the out of sample correlation for doing it with just a classifier is roughly the same as you get with a linear regression model. This is sort of showing that eras can be more or less applicable to other eras. So what we're doing is splitting the eras into blocks of 15, and then training on that block, and then predicting on all the other blocks of 15 eras. And when you do that, you can make a plot like this. And so this is on this y-axis is showing which block it was trained on, and the x-axis is which block it is tested on. You can see that there's some of these early eras tend to not do that well predicting out of sample.
Imagine that.
Yeah, but some of the other ones do quite well. And you can one thing to kind of note is that it's typically pretty green on the left side of this, which is meaning it's easier to predict the past using future data. So because it's basically, if you're training on this one, you're doing pretty well at predicting the past. And that seems to always be true. You're always better at predicting the past than the future, which is not necessarily surprising. But something to keep in mind. So let's see. Well, maybe actually I could just run this.
Nope.
Oh, today. Oh, yeah, I have to restart this notebook. This example is basically just showing that the within sample correlation and the out of sample correlation can be very different. Like your in sample correlation can be like 0.25, like 25%, where your out of sample it can be around 5%. And it's a pretty scary divergence, and something to keep in mind. But it's always been interesting to me that even these models, I mean, your models can have crazy high in-sample correlation, and that doesn't necessarily mean it won't generalize well, which is a little counterintuitive, but that does seem to be the case. This is just showing that yeah, results are very sensitive to your choice of hyperparameters. And so if you're using like a linear regression model or a gradient boosting model, your out of sample performance can vary a lot by your choice of hyperparameters. So you should always cross-validate all of them. So for example, an elastic net model, which is balancing L1 and L2 regularization according to this alpha parameter, you can see that at some values of this alpha parameter, its out of sample performance is pretty decent, about 0.44 compared to just a standard linear regression model. And these are just some of the XG or light gradient boost hyperparameters. And you can see that some of the hyperparameters can give you quite a substantial improvement over just the default parameters. And so, yeah, I didn't really play with these too much besides what was we used originally. With the new data, there's definitely going to be advantages to doing new hyperparameter sweeps.
For sure.
Probably be important. So I definitely encourage people to try different hyperparameters.
Definitely don't assume that your past hyperparameter space is the best. Definitely retest everything.
Exactly. Let's see. So this is just getting back to these ideas of feature exposure. And so if you just train a light gradient boost model and look at its feature exposures, some of the feature exposures are quite high. Like you have a negative 0.45 correlation. This is higher than you've probably even seen in some of the previous models.
Indeed.
So be careful with feature exposure. This is just showing that you can do your sort of standard trick of half neutralizing, and that can bring your feature exposures down somewhat. But even after that, the feature exposure is still fairly high. So another thing you can do is try to be more clever about what features we neutralize. So in Mike's example notebooks, he showed one way of potentially doing this, looking at how features change over split halves of the training set. Another way I came up with looking at what are potentially the riskiest features is looking at what features your predictions are most exposed to, and also which features have the highest volatility in the training set. So just doing something simple like looking at the correlation of a given feature with the target in the training set, and then computing the standard deviation of that as an estimate of like the volatility or how unstable that feature is. And then if you just multiply that by your feature exposure of your of a given model, and then sort by that, you can basically find what I'm calling the riskiest features. So these are the features you're most exposed to and have the highest volatility, which seems like a reasonable definition of riskiest for your model. And then you can try just neutralizing I'm doing a half neutralization to those 100 riskiest features. And that ends up working a little bit better. You get your correlation goes down a little bit, but less so than it did up here, and your Sharp ends up being a bit better than it was by half neutralizing to everything. So being more selective about which things you're half neutralizing could potentially improve your models, or even full neutralizing. These are things to just get you thinking about other ways of tackling the feature neutralization problem. I found it pretty interesting that the maximum exposure after half neutralizing the select group of features is actually a little bit lower than it was when half neutralizing all of them. That was a little bit unexpected, but that's how it turned out. Let's see. So yeah, training on different targets can give you models with different patterns of feature exposure. And this is a great way to try to go after MMC by creating more unique models that will do well at different times. And it can be also very useful for ensembling. So for example, I trained just a pretty standard gradient boosting model on standard target and then target Jerome. And if you just look at the feature importances that come out of the gradient boosting regressor, you can see that they're correlated, but only about 63% correlated. You can see, so there's some features that one model cares about a lot that the model doesn't really, and vice versa. If you look at just the correlation of the predictions themselves, they're about 75% correlated, which is fairly different for. Interestingly, the performance of these two models out on target 12 is usually pretty similar. So as we've said many times, to get MMC, you have to both be different and good. And so like just by changing like your target, you get a model that is basically equivalently good, but also fairly different. So what's one of the reasons that I would encourage people to look at the alternate targets as a way to get MMC. Also, these things can be great for just ensembling. And so this is just looking at the score for the trained on target, both before and after neutralization, and for just an ensemble of the two neutralized versions. And so you can see that after neutralization, the score for the model trained on target is 0.048, and when trading on Jerome, this is 0.05. And I should say this is being scored against target, just target, which is NOMI 20. So training on Jerome is actually predicting target NOMI better than training on target NOMI. But you can see that ensembling both of these together actually gives you something that's substantially better than anything else and has a much higher Sharpe than anything else. So yeah, the different targets are great for ensembling. And so yeah, this is just showing the correlation of the two models that went into the ensemble. And so you can see they're only about 66% correlated after this neutralization. And so yeah, so this, I mean, because it's only 66% correlated and does a little bit better than train and target NOMI, like just a Jerome model will give you pretty good MMC. And yeah, that's I think I finished everything. So
Awesome.
does anyone have any questions or anything people want me to revisit in more detail?
I don't have any questions in Twitch chat, so let's wait and see if our Zoom audience has some questions. Thank you for that, Michael Oliver. Sure. Is your analysis and tips the same as the one that's available in GitHub?
It is, yeah. I added, the only thing that has changed is I am going to add the feature exposure for the different targets can be this little section right here is the only thing I've added since, and I will push that to the GitHub version soon.
Okay, excellent, thank you. AI Joe says, so many things to try. When 60 model spots?
That's an Anson question.
Indeed it is.
Maybe I want to hear more people ask for it first.
I'm ambivalent. I don't think I want 60. That just means a lot more work. But I know some folks really like to test lots and lots of different things and really exotic stuff. So Inversion says more model spots, please. And yeah, so if you all want to see more, you got to do what the slyest of foxes has asked for, and that's harass him repeatedly with requests for more model spots. So he wants to be harassed, then we can deliver.
When model slots marketplace where I can sell my slots to Inversion.
That's interesting. Yes, yes. I didn't even think about that. Wilgumuse with the market solution. Very nice, very nice. We have a bunch of LOLs and Venmo requests flying in chat right now. So look at what you have done.
Anson, how many model slots are we upgrading it to?
Don't know yet. Don't know yet. Right now we're at 30.
Yeah, I've heard a few numbers.
Kind of want to go to 100, but
woo, 100.
We'll see. We'll see.
I think we need to do some like load testing.
Yeah, I mean, basically the trade-off here is like the more models everyone has, the slower our pipeline runs.
What is the average number of models per account?
I don't know, Chris, do you have that number?
I don't have it offhand, but it's something I'm actually going to add to our internal dashboard soon.
Yeah.
So what's the over-under on crashing on Saturday when the data comes out for this round and everyone tries to download it?
Should be fine. Scaled on AWS, correct? Yeah, so it's up to AWS. Should be good on the download function as long as it's put in the bucket. And then the scoring, though, that we'll see, I guess. But it sounds like you've done some optimization over the past several weeks getting ready for this. So
yeah, that was the bulk of my work before the data release.
Nice.
Getting our diagnostics and submissions pipelines up to par.
Jeremy Barros is asking, are any of the new targets already neutralized against new features or subsets of features?
Yeah, no target is fully neutral to the features. As I showed, some of them have kind of very different, like orthogonal feature exposures. But that's not. It means there's just have very different feature exposures, but they're not neutral. Fully neutral targets, yeah, don't seem to work as well.
But yes, some of them are. I mean, like he's saying, is it partially neutral? And I think that is true to say. Some of them are kind of like partially.
Yeah.
They're not designed that way, but some of them tend to have lower feature exposure.
GRB says, Anson Bro, time to set up a GPU cluster for scoring. And there was a question on compute, who gets to see your code? Compute is stored in a Docker image that is uploaded to AWS. Nobody has access to your code. The kernel is uploaded and run in the cloud, and it's just triggered by a web link. And so nobody has access to your code. I don't have any other questions flying in, so I guess we can wrap. I'll just talk slow in case somebody wants to get a quick question in before we go. I want to thank Richard, Michael Oliver, Michael Phillips, Noah, and any other team members I missed for joining today. Kino has a question.
Sorry, John, can I ask a question? Yeah, so what would be like this for the mics?
For the mics.
What would be like, what would you recommend, or like somebody else, like a safe transition to the new data? Because I'm trying to figure out all the things we need to do. And so the first thing is like, the first barrier is like actually like getting the data set to run on our computers, right? Because they're like, you know, we've been having RAM issues since day one, and this is gonna be like probably gonna need like 32 for like bare minimum. But then after that, like, you know, I was wondering if you're just getting the, like say, once I get all the new data, if I get the same scores that are like analogous to like the old data or like my own model, is that like a good comparison? Is that like a good place to start?
Yeah, I think like MDO suggested, looking at like validation 2 scores for the old data. If your new data on the full validation set for new data is like similar or better to your old data validation 2 scores, that's like a good indicator that you're ready to move over to the new data. Does that make sense?
Yeah, that makes sense. Thanks.
Also just to save memory, doing the subsampling thing where you don't train on overlapping eras. And that, I mean, you're cutting the data down by a factor of 4. So yeah, it makes it not too different than the old data.
Right. So I mean, I'm not like very excited about like how this data was released, because like the API path like seemed to me to be more like forgiving for like existing users, where like this, like you put us in this spot where like, you know, there's this giant gap that we don't know if we're gonna like be able to jump over. I mean, what we have like, I mean, I have $250,000 in stakes that I don't know if I should take them out this weekend just because of this, right? But so
you should not do that, because the pipeline will be just fine if you're in compute and you have months to switch over. So that's
right. But then I had like Richard Craig like saying things that like, if you don't use any data, you're gonna like stop. So, you know, it's like, I mean, you're really putting us in some of us, I think, in a very hard spot. And so the API path like seemed to me like a more like generous one. And so my comment was like, okay, we're gonna end up subsampling. Why don't you allow us? I mean, this is like a suggestion, I guess. Like, if we're gonna end up subsampling because of the overlap, why don't you just like include that on the API and say, okay, you know, give me X, like give me the first 3 or like the first 4 of the era. So that way the data set ends up being smaller.
I agree with that.
Yeah, that's something that they said.
The same thing.
Yeah, they announced that they're going to work on the API that's going to come, and that would probably be something that would fit into the API. But there's no API yet, so we're going to have to work with what we got. All right, everybody, thanks a lot for tuning in today. Very happy to see the new data set out. Let's all spend some time and work on it. So on that note, thank you all, and we'll see you in Rocket Chat. Have a great day, everybody. Bye.